So we'll discuss these thoughts on these two issues, and it will probably take about 20, it will take about 40 minutes or so, and maybe we'll have a discussion, extended discussion for about 15, 20 minutes, and then we'll have a we'll come back and discuss this decadal variability, multi-decadal variability. We have discussed about multi-decadal variability briefly in other aspects. So there is one aspect of multi-decadal variability only I want to discuss in this talk. So we'll do that at the end. So let me start then. So instead of taking this, I'll skip these few slides on the multi-decadal variability to start with, and then go over to the thoughts on these two issues. Let me get to that. Give me a minute. So in the conclusion, so I was asked to give my thoughts on two issues. One issue is what does India need to improve the current weather and climate prediction capability, and how the academic community of the country can contribute to this national need. This is a national need. We need to improve our forecast because that has an immediate impact on the people, the farmers, the fishermen, and everybody. So that is the major national need. And there are certain limitations because, and I'll discuss about that, and how academic community could contribute to it. The other important also, we have the whole lecture series has been to attract or induce, if possible, some of the finest academic community in the country to contribute to the weather and climate science problems. And because the climate and weather science community in the country is relatively very small, and there is no really training from the grassroots level, because the weather and climate is not taught in our educational systems in a systematic way, starting from the beginning. But so it is introduced at a much later stage. So there is small, and the jobs in this field is very small. Therefore, there is a number of people, good people that come into this community is rather small, and that has resulted in the progress of this field in the country. And therefore, if we can make some of the fine people in the academic community, and there are a lot, to come and work on some of the issues, some outstanding problems in the that we have in the weather and climate science, which eventually has the potential to improve the prediction system. So these two issues are important issues, and I believe that if we can do something, that will be great. So I thought I'll just share some of the thoughts with you on both the issues. First, let us see what India needs, and what India needs, and for that matter, any country needs, is skillful and reliable prediction of weather and climate. Weather maybe day-to-day time scale, and seasonal climate is seasonal mean. Now we are talking about sort of climate projections, which is also another something like prediction, but not really prediction, because you cannot predict freely for very long time. But if we know the forcing, and if the forcing is given, then probably we can project the climate to the future, and that is required for policymakers. And so that is also an important science question. So this is something required by users and policymakers. So but And today's, so how did the skill of forecast have improved in the past? Skill of the forecast have improved in the past, especially for weather. Today, weather forecasts have excellent skills, and these weather forecasts have improved basically to fundamental research in atmospheric and oceanic processes. Understanding of this research have helped us to improve the forecast models. Forecast models require physics to be incorporated, the effect of small scale physics on the large scale phenomena to be included in a parameterized way, and that parameterization has to come from basic understanding of these processes, and that is the very key to improvement of models. Therefore, the fundamental research is very important for improving the forecast models and therefore forecast skill, and that has been is a key for improving weather forecast. We also continue to do research on phenomenology, but that is required because we always find out, because we still don't probably have not known many different phenomena and variability in the atmosphere and the ocean, which is buried inside the lot of noise that is there, and we probably have not seen them, and they may have their own influence on our climate and weather, and which we are missing. So this kind of research, this is a kind of blue sky research in atmospheric and oceanic science, which we have to continue. We have to search for signals of variability and phenomenology, which are unknown today, and that will continue. But apart from that, we have to, including those new phenomena as well as the currently known phenomena, we have to continue to do research on understanding the details of them, the nonlinearity of them, so that we can improve the models and we can incorporate them correctly in the models and therefore improve the predictions. So therefore, in order to understand these, the forecast is always is done by a forecasting system. So therefore, in order to understand how we can improve the forecast, we have to understand what is a forecasting system. So let me go through it very quickly. This is again a very pedagogical in a sense that it is very introductory, but I think for the people, just to get a sense of what we need to do, we need to understand what is a prediction system. Let me talk about the weather prediction system. Weather prediction system essentially have a forecast model. The forecast model is nothing but those basic equations that describe the motion in the atmosphere and the ocean, and that is driven by the heat balance. That the heat balance it has a lot of physics inside, and once we can calculate what is the heat balance at its point on the earth, then we can find out what is the pressure gradient, and therefore that will move the air and therefore produce motion. And so all that is in this forecast model. Now the forecast model has to be initialized because you have to start from an initial state, and that state has to be advanced in time to produce forecast. So to start the forecast, you need to initialize the model with some initial state. Now initial state comes from observations. Observations comes from the conventional observations and satellite observations. All that is used to derive what is the initial state, which is described by the winds, temperature, humidity, surface pressure, and maybe sometimes some other new variables that we are introducing today, like aerosols, for example. So if anything that we are doing, and the ocean, for example, biogeochemistry, and all kinds of other new things that we are introducing, those also have to be initialized at every point of time. So for that, we need observations. And then once the observation is obtained on real time, that data then is analyzed and then put into regular grid points and used as the initial state for the forecast model. And then forecast model then use the time marching and produces forecast at a later time with of the same state of the state variables of the atmosphere or ocean. So that is the forecast basically. So this is, so the forecast model is key, and the initial conditions are also key, because the initial conditions which come from observation provide the initial state. But if the initial state does not provide a very balanced initial state, which is required by the equations of motion here, once you put this initial state in the equations of motion, they may not, because of the observation errors and analysis errors, they may not actually balance the equation. Therefore, the imbalance will look like an initial error. That initial error then grows with forecasting times and deteriorates your forecast. Forecasts go away from observations, and therefore that becomes a problem. So our forecasting skill depends on accuracy of the initial state and how we can make it properly balanced with the equations of motion. So that is, so therefore, briefly, schematically, if we can say that it has two components. One is a dynamical core, and the forecast model has a dynamical two components. One is a dynamical core. Dynamical core means the basic equations of motion. So these are the basic equations of motion. So just let me just I will flash it out. I'm not going to details, but these are the Navier-Stokes equations, basically momentum equations, temperature equations, equations for humidity and continuity equation, and the surface pressure equation, which is essentially a integral of the pressure at that point. And they are forced. These are terms which are essentially forcing and dissipation. So in the temperature, in the humidity equation, there will be source and sink terms, which will be forcing functions. Like the precipitation will be taking out humidity, evaporation will add humidity, therefore source and sink will be there. So those are essentially forcing. On the temperature, the heating will be forcing, but there will be dissipation, turbulent dissipation, and mixing, which will essentially be the dissipation. So this whole thing is the dynamic core. So that is the dynamic core. So, and this part, this physics part is related to all kinds of physical processes, like how clouds form, clouds give heating, the boundary layer turbulence gives a mixing of moisture into the upper atmosphere, and so on and so forth. So all that physics is included in this term, and that can be considered as a physics module. A physics module have all these different components, and these are all different modules that contribute to the heating in a different way. The boundary layer, the moist processes, radiation budget, the lateral mixing, and these moist processes have to be parameterized, because some things are resolved, but some processes are unresolved, because the model has a certain grids, and that grid cannot resolve certain small scale processes. So the subgrid scale processes have to be parameterized, and that is a major issue here. And so this is the kind of structure. Let us just keep that in mind. Of course, as we go to the same thing is there also for our the climate prediction system, like seasonal prediction system. But it has more complexity coming in, model complexity. Like we have to couple it to the ocean, so it will be ocean equations and ocean physics that will go into that. But we can also have biogeochemistry and ecosystem carbon cycle chemistry in the ocean, so that all needs to go as complexity of the climate prediction system. So, but basically, conceptually, the structure remains same, and the challenges may be a little bit different. So there are, of course, a lot of challenges in solving these models. The resolution is one big challenge, because it has to be solved over the globe, and depending on what resolution you can afford to solve it, the number of grid points on which you solve all the equations in the horizontal direction as well as in the vertical levels. So these are a lot of levels in the vertical, which will both increasing the resolution in the horizontal increases and vertical increases the accuracy of solution of the basic equation, because you basically these equations are numerically solved by using certain difference techniques, and therefore their solution, the accuracy of the hydrodynamic pore depends on the resolution to a great extent, and therefore we want fine resolution. But as you go to finer and finer resolution, the cost of computation becomes very enormously big. It goes as n to the power 3 rather than n square if you double the number of grid points in the horizontal direction, because as you decrease the resolution, the time step that you have to use for integrating also has to be reduced to for computational stability, and therefore actually you increase the computational cost by n to the power 3 rather than n square. And therefore, it is a challenge that we need. But with the better and better computers available today, I think we are able to now go to very fine resolutions and still produce useful solutions. Then, of course, the physical processes, as I mentioned in earlier time, that they are very complex. There are many scales involved, and therefore, these the physical modules require certain approximations, and that makes certain errors that go into the model, because as this parameterization, so this all this physics coming from clouds, the land surface processes, the stratospheric chemistry, radiation budget, of course, long wave, short wave, and aerosols, boundary layer turbulence, all these influence the heat budget at every grid point, and therefore that has to be calculated. But each of these involve different scales, and that and then the effect of the unresolved scale have to be taken into account to calculate the heat estimated the heat produced by these processes on the resolved scale. And so that requires what we call a parameterization, because for example, clouds normally, let us say 50 kilometer by 50 kilometer grid, but many clouds are the thunderstorms are smaller, like 1 to 10 kilometers. Some of the cumulonimbus clouds, and they contribute. The ensemble of those clouds contribute the amount of heat that is released in the 50 kilometer by 50 kilometer grid box. So how do we estimate that? So for that, we'll have to parameterize. Now, how do we parameterize? Parameterization is nothing but how the small scales depend on the large scales, and how small scale clouds depend on the large scale environment. So you have a background, one value for each of these grid points. So that represents the winds and the humidity and temperature value of the larger scale environment. At that environment, what kind of statistics of clouds we expect? How many tall clouds, how many medium clouds, how many shallow clouds will be there? And if we can predict that, and then we can actually calculate what will be the vertical distribution of heating, and that will then can go into the and so therefore we need to understand that requires basic research. And once you understand that, then we use a certain formulation or parameterization to do that, and that has to be done for all the different components of these physics packages. And then there is, of course, the observations. The observations, as I mentioned, are analyzed. Now there are a lot of gaps. Therefore, the analysis will have errors, and those errors. And I have discussed this analysis in the first one or two talks. And so these errors have to be minimized. Now, how do we minimize that? That is what is data assimilation, or the data assimilation, or the method. The data assimilation method essentially tries to minimize the difference between these, the constraint where there is no data, you constrain the model. They constrain the model to give data which is constrained by whatever observations in the other places. So, so we have to somehow minimize these differences. That is, and that minimization between what is expected by the model and what is given from the observations of the first case is essentially the assimilation practices, and that has improved over the years, and that has also reduced our initial error, and that reduction in the initial error has now improved our forecast. That is one important thing. Other thing by which we have to also reduce the uncertainty in the forecast is because of the chaotic nature of the atmosphere and even ocean. So they are essentially dynamics is deterministic chaos, therefore they're sensitive to initial condition. And because there is all these errors in the initial conditions, so the evolution of the trajectory is going to be different from observations. And therefore that will lead to error, prediction error. And because but if we have just one prediction, one member prediction, then you don't know whether that is the kind of average that we will have if there is an ensemble of errors in the initial state. So what we normally do is that if you create an ensemble of forecast rather than just single one deterministic forecast by perturbing the initial condition, because we know that there is a certain amount of error in the initial condition. So we assume that there is a sphere of errors in the initial condition. And if we had this sphere of errors, then what would be the different ensemble states of prediction? And then you do an average of these ensemble states and in the hope that they will give me the most expected state of error, expected state of prediction, and that is expected to be closer to observations. And because they will sort of eliminate because the randomness of the initial errors will give rise randomly. The initial states evolution will be randomly distributed, and therefore the average is expected to give me a better forecast. And that is what also it gives you a probability because all these forecasts actually have to be probabilistic because of the chaotic nature of these. And therefore, if I have a large ensemble of forecasts, it gives me a probability of different possibilities, and that gives me what is the most probable forecast. So that is so that is also required. It also requires as a result, it also requires competition. Competition cost goes up. But all these things have helped us to improve the forecast. So there are two sources of errors in the forecast. One is the initial error, and the other is the model error. Model error comes from the physics as well as from resolutions. And the initial error comes from the improving the analysis. So it can be by data assimilation. By improving the data assimilation, we can reduce this imbalance, initial imbalance. And if the initial error is reduced, then it surely helps us in terms of the prediction, the forecast. But model error is more important because the models is used to integrate these two for a long time, and therefore for all these, let's say, 10-day forecast, every time step model is going to add error. So therefore, the reduction of the model error is quite very important. So the reduction, the resolution actually makes a big difference. Because higher resolution does two things. One is, of course, it improves the simulation of the solution of the basic hydrodynamic equations, but higher resolution produces better resolution of the topography over the globe, and the topography influences the rainfall. So therefore, if the topography is very poorly resolved, it really makes a big difference in simulating the local rainfall. And that is a big error. And therefore, Therefore, it is very important that we have as much as high resolution as possible to resolve the topography. And if the topography is resolved well, you can expect a much better simulation of the rainfall distribution. So that is important. So therefore, with all these three different effects, actually over the years, how the improvement took place is better observations became better and better because space-based observation came, so that analysis became improved. Now we improved also the data assimilation effect. And so and these two things have reduced the initial error. Then with better and better models have improved tremendously over this last 50 years. The complexity and the parameterizations have steadily and steadily improved in almost all the different aspects of physics, and that has contributed very significantly. So, and this has been possible to do because of availability of better and better computers, and that is the computers. Even in India now today, we have very supercomputers at IITM and also at NCMRWF. So these have definitely have helped us to put this into effect. And so we have to recognize that all these three things are required to improve forecast. And this is an example of how how data has actually has improved forecast. For example, this is this is a European Center forecast. Okay, this is a history of European Center ECMWF weather forecast. This is a leading center in Europe, and they have good history of forecast from 1980s today till today. This is southern hemispheric forecast in the extratropics, 20° to the pole region, and the scale of southern hemispheric forecast and scale of northern hemispheric forecast. This is 3 day ahead of time, 3 day lead time, 5 day lead time, 7 day lead time, and this is about 10 day lead time. Okay, so today your forecast at a 3 day lead time is almost 98% accurate, and both northern and southern hemispheres are almost equally. But you remember that the traditional data, the radio sounders are not there. This is because of the ocean. There is no data. As a result, in the early days, the forecast scale was at all lead times was much poorer in the southern hemisphere than in the northern hemisphere. But today they are identical. That is because of the satellite data is now giving very high resolution temperature profiles, and these temperature profiles give geopotential profiles, and therefore they give the winds also, because the higher latitude they are geostrophic. So by getting a very high resolution lot of data from satellites, that has become as good as conventional observation, and therefore you don't need conventional observation in the extratropics, southern hemispheric extratropics. So this is the power of observations, and that satellite observations have shown that. And but there is another aspect of this improvement, that is, suppose you ask this question, how what is the importance of observations versus the model? Now, in the old days, models were also poor. Their poorer resolution, physics were poor, and therefore more errors were there. And that is the sum of the poor scale in the older in 80s were due to both. Now, suppose I ask this question. Okay, let us take this today's model and go back and make forecast doodle model and the forecasting, the data assimilation system. Data assimilation system is also very important. So if I take that data today and go back and actually make retrospective forecast in 1980s for 3 day ahead, 5 day ahead, etc., you can see that the 70% scale has gone up to 95% scale today. That would have had 95% scale instead of 70% scale if we had the good model. Data remains the same, because at that time the data is you did not have any new data. Let us say you take the same data but use the model to do an assimilation scheme, then it would have increased significantly, and there the difference and the growth is of the skill is very small. So the model actually is a very important part, and this is something that and many of us, many people did not want to realize, and I think this is something that we need to realize, because that is where we have to invest more resources. So now, how do you, the important lesson from this is that the model development is, forecast model is much more important than improving the skill, in improving the skill of forecast. Data observations are important, no doubt about it. And assimilation scheme is required, and we have to improve that, because that initial shock is very important. We have to reduce the initial shock. But the model is far more important. Therefore, we have to focus our energy on model development and improvement. So how can the country, what is the country's status today? I think I have to, so let me, so now let us, with that background, let us see how to improve this skill, how to improve this forecast skill in the country. Now, this is also a very important point, because we have to recognize that the forecasting is always done by the operational agency, right? The private people cannot do the forecast. Although today there are a lot of people, players are coming and giving forecast, they cannot really do the research in forecasting. They take forecasting data from research, other centers, operational models, and then produce their own forecast and give it. But essentially, most of the forecast is done by operational forecast agencies in the different countries, and therefore there is an operational forecast model. And that operational forecast model produces the forecast that requires all these infrastructure, data assimilation scheme. You have to collect the whole global data, analyze it in real time, and also do research on data assimilation to make it balanced, and then make the forecast, analyze the forecast, and give it to public. So all these things have to be done by an agency, and that is what is done, because most of the private players cannot do all this data collection, and they cannot do the data analysis and improve the initial conditions. So that is not possible. So that is done by one agency, and normally it is done by a forecast agency. So therefore, improvement of skill forecast in the country has to come from the improvement of the operational forecast model, and this is a key. And a lot of research we can do in the academic institutions, but that may not add to the improvement of forecast because of the disparity in the models. And therefore, academic community also have to work on the forecast model improvement, the operational forecast model improvement. So each weather prediction model and the climate prediction model is different slightly, because the difference in the physics modules and parameterizations, they include different physics modules and different parameterizations, and these parameterizations of different models are somewhat interdependent, because, for example, cloud parameterization is often important, is related to the radiation parameterization, because radiation and cloud are very much linked, and therefore a error or bias in the cloud parameterization will affect the radiation balance, and therefore it will not work unless we have to have a synergy between all the different parameterization, and that can happen only if you do development on a given model, and that is why we need to do on the development on the forecast model. So model development must be done on the country's operational. This is the important point that I wanted to make. So having said that, now how it is normally the operational agency or the model research and development group model normally have the model research and development group. Unfortunately, IMD does not have, because of the human resource problems, do not have a big in-house group. Therefore, they are also assisted by the countries a few research organizations which help them. For example, in NCEP, USA is supported by NOAA and GFDL, Princeton University, and NCAR has a big lab, and therefore they have a lot of research, basic research, which then feed back into the model development. In India, of course, IITM is there, and IITM was set up for this purpose in 1962 to do basic research and help IMD in all aspects, including model development. But unfortunately, over the years, somehow the synergy between IITM and IMD drifted apart for various reasons. I don't want to go into details, but as a result, there is no linkage or research that went in IITM go to IMD or vice versa. When I joined IITM, and our state of prediction system was pretty poor. We had a deterministic weather prediction using a T20 atmospheric model, which is about 150 kilometer resolution, and no dynamical model whatsoever other for couple model, no dynamical couple model in the country for either seasonal forecast or extended range forecast. So we had we were in that point. That is why I sometimes say that we are behind at that point about 25, 30 years compared to the rest of the world. Elsewhere in the world, how the advances took place. The advances took place basically through one important part, as I mentioned, is the supercomputing capability. Without supercomputer, and you cannot do higher resolution models, you cannot do many experiments, and therefore you cannot, development itself is inhibited because the development requires a lot of experimentation, and therefore you need a free availability of computational resources. So that is an important part. But in India, what happened that from 80s to about 2000, middle of 2000, after 2006, we had very little computing facility in the capability in the MOES organizations. Total computing power was less than 1 teraflop, whereas the forecasting centers elsewhere, they were of the order of a petaflop. So you can see that you could not do much work, in fact. So that was a serious issue. There was also a important issue about our community itself. I think the Monsoon scientists, a lot of senior Monsoon scientists, and IMD leadership did not think that improving forecast model is the key part about, and they were more focused on observations. They were observations, improving observations will improve our forecast. So I think this was a very key conceptual problem that was also limiting our growth in this. So as a result, what happened is that we had the problem in essentially building capacity in the model development, and that was a big issue. So then something happened in 2006, which was really historic, and MOES was born. And this brought in the important differences. This MOES brought in synergy between these organizations. The IITM, IMD, and CMRWS and NCOES actually MOES created a certain amount of synergy, and that was great. And through Monsoon mission, it was sort of encapsulated. And as a result of that, and the Monsoon mission put a lot of sort of measure plan in capacity building, training a lot of people, a whole bunch of young people in model development, and that plus an ambitious long-term plan for computing capacity building was put in place. And I think this is what made a big difference in the next 20 years. And this was actually, I must say that I must thank Dr. Shailesh Nair, who had a vision and tenacity to support the Monsoon mission, and and convince the policymakers, because there is huge, several big important policy was required to be supported. For example, we are breaking away from this idea of building supercomputer in-house and allowed to buy it from outside, which was something that MOES was able to convince the government, and Lesnagar was kind of instrumental in doing that. And he was able to also generate the resources required to do the other things that was required, do basic. So this is something happened, and so I think this is something remarkable happened during that period, where the computing resources if I look at the history of IITM computing resources, when I joined, it was like less than 0.1 petaflop, teraflop computer. We had a Sun solar system, and then we through this long-term plan, we increased in 2008, 8-9, we increased it to 7 teraflops, 70 teraflops in about 10, 11, and 800 teraflops in about 2013. And by 2018, it went up to 4.5 petaflop. All this planning was done during that time itself, and this arrived after I left, but still the approval of this was done during that period. So this actually made a huge difference, and together with that, now the NCMRWF also has a 2.5 teraflop machine. So I think computing and capability is right now quite enviable. While there is, of course, this also brings responsibility. So we should be able to do much better research, not only the forecasting, but also basic research using this computing facility. So what happened in terms of the forecasting capability? Also, IMD during this period, about 5 different state of the art. Today we can call the IMD's capability of forecasting almost a state of the art, in the sense that we have a weather prediction model, 12-kilometer weather prediction model. This is based on the NCED CFS system, atmospheric component, but it does a global 12-kilometer model and deterministic forecast. Deterministic means just one member for ensemble. Then it has an ensemble forecasting system of weather, where you have a slightly lower resolution atmosphere, T512, which is about 35 kilometers. It makes a large number of ensemble for each forecast, ensemble for each forecast. And that forecast gives you a probabilistic forecast. And because of the probabilistic, also the large scale weather systems are much better predicted today. To get the smaller scale system, some idea of the smaller scale system is given from the high resolution weather forecast, but then there will be due to the chaotic nature, there will be certain errors in that. But to improve that, you have a regional model that runs within these, using the boundary conditions from the global model. And that regional model is called WRF model, which is actually not a same physics as this, but I'll come back to that point in a minute. So, but it also gives you a better, higher resolution forecast in whatever there is weather active region is there. Then you can run that model and you can find out, give a better forecast of the weather systems in that model with higher resolution. Then we have a seasonal forecast system using couple models, CFS. These are all run operationally today. Then you have an extended range forecast, that is like forecast you make up to about 1 month or 45 days ahead of active and break conditions, and that also uses the couple model. So all these systems of forecast were essentially developed or built, tested at IITM, and then transferred to IMD to be operationalized. And by about 2014, all these 4 different forecasting systems are operational in IMD, and that make the sort of whole ecosystem for prediction for IMD, quite state of the art, I must say. People who actually understand this, this is in this time scale this happened. This is not non-trivial achievement from MOES. It is a very big achievement, I think. And I think this what is important also happened during this period is that many of these institutions in the under the MOES started working in kind of as one unit, helping each other, and keeping in the sort of goals of each other's in sort of as tied together. So this is good to see that also today. I think IMD and IITM do not talk about two different entities. They talk about. I think this is something that is very, 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 very good to see, and I think this is something that happened over this last year. So IMD has, in addition to that, IMD has a tropical cyclone forecast, which they developed mostly from in-house, which is pretty good. It has a very good skill actually. And it was helped by some academic institutions like IIT Delhi, where Professor Ishi Mohanty made some contributions on this. And then, of course, the in-house work at IMD also improved several things. And therefore, today, the skill of IMD tropical cyclone forecast is pretty good. And what happened during the monsoon mission is that the global model boundary conditions improved, because now we have a higher resolution global model, and these global models are also now giving us better forecast, and therefore that model, that large scale component which goes in boundary condition improved. As a result, the tropical cyclone forecast also improved. So this was a kind of synergy. So in addition to, during this period, IITM did a lot of in-house development of this model. See, philosophy of development of model was that at that point of time that we don't reinvent the wheel. We bring in some model and bring in some model, but the models, as I said, are always incomplete, and there is always a lot of scope for improvement, and start a development on that model, and that is what was done, and we started, and we should continue that, and because if we start doing modeling development in other models, 2-3 different models, none of them will improve. We have to continue improvement, and over many years, only a model becomes better and better, and finally it becomes our model. And for that, we had done several important improvements. I don't want to go into details, but this is a lot of work had gone in, and that had improved all this work over a period of about 7-8 years was required to improve the scale of seasonal forecast from about 0.5 to about 0.7. It's always incremental, but that incremental change is still very important, and that is what we have to continue. So how we cannot relax, and then we have to actually improve on this. There are two things that let me quickly go over. I think it is taking a lot more time than I thought. Okay. What should be done? What should be our strategy for model development? This model development strategy must be working on this GFS and CFS system only. We have to work on that, and must concentrate on development. We have already added some development there, and some really improvement have shown, but we must continue to do that. But there are two issues that are important required in this model development. One is that this particular model is called hydrostatic model. It is not non-hydrostatic model. Therefore, this model cannot be used to simulate thunderstorms, for example, which is non-hydrostatic process. And therefore, we need a model. We have to actually convert this model to a non-hydrostatic model, so that for global model, lower resolution, let us say even 15 kilometer global resolution or 12 kilometer global resolution, we can use a non-hydrostatic. Actually, hydrostatic model becomes not very applicable on a 12 kilometer global model, because then almost we are resolving some clouds, and there actually we want a non-hydrostatic processes too. So that is one issue. Or even if we have a something like the 20-kilometer global model, but to simulate the regional regional climate weather much more with a higher resolution model, the regional model must have the same physics and same everything. Therefore, a version of this GFS model, which is non-hydrostatic, can replace the WRF, and it will possibly reduce their error and therefore improve the regional simulation. So therefore, we need to go into a non-hydrostatic model development or based on GFS, CFS. There is also an important part. Over all this period, we have not done much improvement on the ocean model. And ocean model has a lot of biases in the simulation of the Indian Ocean SST. And improvement of the physics and mixing in this is very important, and there are some biases, and I think we need to do improve the ocean model component of this, and this is something that has been missing and we need to do, and this is very much concentrate in my opinion. So how could the academic community contribute this? And of course, they can contribute in focusing on this model development in terms of improved parameterization. Parameterizations maybe in the cloud microphysics. Stochastic cloud model is the kind of upcoming area which is expected to improve our cloud distribution simulation, and therefore that is area where we need to improve our parameterization, and then of course there is a scope for improvement of the boundary layer, particle mixing in the ocean, and ocean model development. All these areas, there could be contribution from the academic institutions. But I have a sort of concern based on my own experience, that the academic community, so the model development is essentially a very slow process, and it is a time consuming process, and it often does not lead to I make a hypothesis, I start developing a model, and then at the end of it, it may not have improved their forecast. Then you might you may not get a good paper out of it. Actually, you should get a good paper out of it if I do it analysis properly. So so the academic community might have a problem in investing enough time in the operational model, because and I have found that during my Monsoon mission, most of the academic community stayed out of it because they felt that it is not sort of, because they have their own comfort zone where some of them are actually working on some models, but then they're not the models that the operational agency wanted to do. But our goal in the Monsoon mission was that we'll give a project to various different organizations who can work on this model and come back to us about telling us how it can be improved. So that did not happen, and I fear that academic committee may have same kind of issue in this kind of simulation, in this problem. So and I'm not saying the academic community is only to be blamed, but it has to come from the other side also. Must feel from the MOES and the institutions of MOES, the leadership must feel that whatever the resources they are going to invest in discussions and these are going to be fruitful, or has at least potential to sort of, and should not feel that they already have everything they know, need, and don't need this kind of a collaboration. That is also possible sometimes. You can it depends on the leadership, and then you will have a problem. Also, they have to really be convinced that this interaction will lead to something that will be useful for them. So I think it will require, as Professor Sankar told me offline, that I think the devil is in the detail. We need to have to discuss this and brainstorm between the academic community and MOES organizations to come to some sort of come to a clarity on what we can collaborate with, fix some specific problems, and then there is a potential. I think a lot of talk is required. I think this is something that is important. So, and then and the other outstanding issues that also I was requested to make, that okay, forget about the operational model, operational model development. That is one issue. The forecast improvement is one issue, but there are also other issues of climate science where academic community can actually contribute. And I feel that there are 4 or 5 issues that I think are important. Complexity in the climate science is what I feel is one of the issues. Over the last 70 years, I think we have sort of understood some of the simple models of for climate phenomena such as El Nino, Indian Ocean, etc. But all these phenomena are non-linear. The event-to-event variability is very complex. And we don't know, and that event-to-event variability actually limits the predictability. Therefore, we must understand this event-to-event variability. What produces the event-to-event variability or the complexity? What kind of nonlinearity determines that? Is there some pattern on that of this low-dimensional chaos? So we need to figure this out, and there is a research that is required to and since the physics community and many of these physics and astrophysics and many are very much familiar about these complex problems, and maybe we can learn how to deal with our complexity from the physics complexity. And somebody also asked me that how AI/ML can improve the prediction, and I think there is also a great potential for AI/ML, because the linear models have their own problems, they are overfitted, and they cannot do the non-linearity. The GCMs have their all biases, and these biases are not going to improve very immediately. This will take ages or decades before they can slowly improve. Therefore, in the meantime, I think the AI/ML model can help us by using whatever model output we have to train them, and whatever observations we have, a combination of the observation and the model output can train AI/ML model to capture some of this non-linearity, which is actually affecting our limit on the predictability. And so if you can understand that, then you can make a model. So for example, so what is the nonlinear dependence of the initial state of the predictor at different lead times with the final predicted state of the ISMR? I think this question we don't understand. This is something like a nonlinear pattern recognition problem. And so if we can do something in this through collaborations, I think this will really help us push our develop better empirical models, which is physically based on learning the nature of nonlinearity from model simulations as well as from observations, and using them in an empirical model to improve forecasting. There is this thing. Then there is signal to noise problem. There is one general problem in atmosphere is of course finding good signal from which is buried among atmosphere. But I know that the physics people have a lot of experience in finding small signals from noise, and I think we can learn a lot from these. This is some area where we can actually also collaborate. Now the latest, I think, I think what is the kind of the frontier in our research? I think the frontier is research is the decadal predictability, and this decadal predictability and the decadal multi-decadal variability, and this is what we have to concentrate. And this is where there's still a lot of work is required, and this is an area again where we can collaborate in terms of understanding the decadal multi-decadal variability. I forgot. I think one last slide I added, which is somehow missing, is that another area where physicists can help us in observation. In one area, observed area is where that something is required and is still not available, is a development of a satellite-based, space-based vertical profile of winds. See, the winds are, now we have a very good very good vertical profile of temperature from space. And that has created whatever the improvement that I have told you. But in the tropics, the temperature and winds are not related, not coupled that strongly, because of the, it is not geostrophic. Therefore, the temperature measurement does not give me wind measurements. And over the ocean, the low level winds are very much important in initiating the disturbances, cyclones and other things, and that data is not available. And therefore, we need a profiling of winds from space, and that can make a big difference. Unfortunately, this has not happened because there are issues about the radar taking up space and active radar having power problems and all kinds of other problems. There are a lot of other issues. I think the astrophysicists also have a lot of experience in terms of profiling other things, and I think we can collaborate even in this. This is something passionately I have been arguing, and nothing has happened over the past in the country. ISRO was interested, but somehow our academic community has not been able to push it further. And maybe this is an area where again we can initiate some discussions. So with that, let me stop here. And